to talk about some curve sketching techniques for section 11.4. We're going to combine everything that we've learned so far, plus maybe algebra concepts about asymptotes and domains and stuff. So let's get right to it. All right, so for this function, we want to know what the domain is, right? And then some of the intercepts. Okay, so the domain for this function. So notice that we have a square root. So what do we know about square roots? Well, we can't put a negative number in under the radical, right? That's not really allowed. So usually when we have a square root function, it kind of looks like this, where our domain is like all positive x's. If this was just y equals x, square root of x. So now we have square root of x plus 100, where x plus 100, whatever's under the radical, has to be greater than or equal to 0. It cannot be negative. So then this means that x has to be greater than or equal to negative 100. So in interval notation, this is negative, I suppose 100 is included. Negative 100 is included, and then this goes to any positive number. Because if we put in negative 100, we would just get the square root of 0, which is just 0. So negative 100 is included. And that's your answer for the first one. All right, x-intercepts on the graph. So let's say here we're shifted to the left 100 units, but anyway. So maybe something like this. So we want to know, where does it hit the x-intercept? So this occurs when my y is equal to 0. So my y is equal to my function f of x. And where is this equal to 0? So I can square both sides to undo that square root and get x plus 100 is equal to 0, or where x is equal to negative 100. All right. And so my y-intercepts are where my function crosses the y-axis. Okay, so this is where my x is equal to 0. And so this occurs when I plug into my function 0 for x. So usually this is the nicer of the two to solve for, because now you're just solving for y. So y is equal to square root of 100, which is 10. Okay, so 10 here. Okay, so new function. Here we have 39 over x minus 3. So again, we do have a restriction on the domain because we can't divide by 0. So the denominator when x is equal to, the denominator is equal to 0 when x is equal to 3. That means that I can't have the number 3 in my domain. Right, because if I plug in positive 3, I get 3 minus 3, which is 0. 39 divided by 0 is not allowed. So that's why our domain's restricted here. Again, x-intercepts, let's find when y is equal to 0, where y is my function. So we can multiply both sides by that x minus 3 to get rid of that. And notice that there are no x-intercepts, right? So, right, and we can kind of tell just because our numerator is positive, so it doesn't have any way for it to be 0. So that's why this one does not have an x-intercept. And y-intercepts are when my x is equal to 0. So I want to find y when I plug in 0 for x, and so I get negative 13 for my y-intercept. Okay, so we have the graph of f here, and we have quite a lot of parts here, but I guess I also had these assumptions here that the second derivative of 0 is negative, second derivative of b is positive, and second derivative of g is positive. So that's concavity, which kind of makes sense. But anyway, so we want to know the intervals on which f prime is negative. So when f prime of x is negative, that means my f is decreasing or increasing. So that's where my f is decreasing. So let's look at our graph. I see if we go from left to right, we're decreasing on this interval. Then we go increasing, increasing. We're decreasing here on this interval from m to this, or not m, to 0 to e. That m is referencing this height, I imagine. But anyway, decreasing here. And then it seems to be increasing everywhere else. So this gives us the intervals negative infinity to this b, and 0 to e, and e to g, just reading it left to right. Okay, so let's work with the same graph. Now we want to know where f prime is positive, so that means my f is increasing. So let's look. It's pretty much just going to be the intervals we did not name, but we can just do it for good measure. So it's increasing there, also increasing from d to 0, and increasing g to onward. So my intervals are b to d, d to 0, and g to infinity. I always write it like that, g to infinity. Okay. So now we want to know when is f increasing, and it's actually what we just did, right? We just found where f's increasing. So it's pretty much these intervals. And they, for some reason, ask it again when f is decreasing. So that's what we found here. F is decreasing with, or when my f prime is negative. So it's going to be these intervals, which I'll write again for you. E to G. Okay, so maybe they just asked you that again just to draw the connection between the two, but they are the same, corresponding to each other. All right, so we want to find the x-coordinates of the points where f has a local maximum. So select the correct choice below. All right, so we are given f, the original function, so we can just look directly and see I have only one local max, and that occurs at x equals 0. Okay. Let's do a few more parts. I know this one's kind of long. All right, so we want to look at where f has a local minimum. And so again, this is f, so we can look directly onto the graph, and that's at b and g. I have 2. Okay. So now we want to know where the intervals in which my f double prime is negative. So my second derivative is negative. This means that my f is concave down. So inverted upside down bowl, however you want to think about it. So graphically, let's look from left to right. This looks like concave down to me. And then, let's see, well, this actually looks concave up. So it's actually, I know it's kind of hard to tell on here, but it's actually from here, from negative infinity to a, because then this stretch is actually concave up. And then it's the same thing over here. It's kind of concave up, and then it changes concavity at h. Which, spoiler alert, that means that h is a point of inflection, so is a, but we'll get there. But anyway, we are looking at concave down, so not these pieces. And then we also have this piece right here in the middle. That's definitely concave down. And so these intervals here are negative infinity to A, and then that middle piece D to E, and then our last interval, H to infinity. And so now F prime or F double prime is positive when F is concave up or down? Up, right? And so these are the intervals that we basically did not name, right? Where we're concave up from here. Try to make it more defined, and then also here to H, remember, because this is all like a right side up bowl. Okay, so these corresponding intervals are A to D, and then E to H. And you can kind of see that they're the intervals in between the intervals in part G. It's another way to look at it. Might not always work out that way, but that's how this one is. And so, oh, it does it again. So they want to know when the graph is concave upward. So we just found that in this part before it, right? So again, I guess just drawing the connection between F double prime being positive and F being concave up, I guess. That's why they're making you rewrite it, I suppose. But anyway, you can just copy those down. And then I imagine the next one, yep, it says concave downward. So that's where we found this right here, right? Because these two are the same. So we have the intervals from that question, negative infinity to A, D to E, and G to infinity. Okay. And points of inflection. So I hinted at it last time, but it will be this A and H because it's concave up and then it goes concave down and concave down to concave up. So concavity changes there at H and A. All right, so now we want to look at horizontal asymptotes. So we have one and it occurs right here. Right, because it kind of seems like the end behavior as this function goes on, it approaches that line. And so we have to type an equation, so that's going to be y equals L. That forms my horizontal line or horizontal asymptote. And vertical asymptotes. So that is where we have these vertical discontinuities here, right? Infinite discontinuities. And so these take on the form in equations. We have two, right? So the leftmost is x now because this is how we write vertical lines. X equals D and x equals E. Alrighty, so I think that's that for that question. That was a lot. Feel free to go back and review any part that you didn't understand. Okay, so now we kind of did something similar to this, I believe, in the last section where we were given two sign charts and had to figure out the graph, I believe, right? We want the graph of F. Right, so I always like to put the interpretation from these sign charts into words in terms of what I'm trying to graph. So in this case, F. So my F is increasing on the blue intervals for my first sign chart. So from -4 to 0, and then 4 to infinity. F is decreasing on those gray intervals, basically the intervals I did not just name, right? And then for my second sign chart, this second derivative sign chart will tell me about concavity of F. So F is concave up when my second derivative is positive. And so this occurs between -8 and 0, and then 0 to 8, and then it is concave down in the intervals I did not name, in the gray intervals, negative infinity to negative 8, and 8 to positive infinity. Right, so now I suppose we were also given some other information. Our domain is all real numbers, and we have this limit as x goes to positive and negative infinity, we approach 2. So that actually talks about end behavior, right? This x goes to negative infinity as my x gets really large or negative all the way to infinity. My function's approaching 2. So that kind of rules out A and B, I suppose, right? Because that means that I have a horizontal asymptote. Horizontal asymptote at x, y, right? Horizontal at y equals 2. So that's why C and D have to be, or one of them has to be one of our answers. Okay, so let's look at f is increasing from -4 to 0. So I think each of these are 4 units. So -4, let me use this color. -4 is here. So if we're increasing from -4 to 0, well, we're decreasing here, right? So that, oh wait, hold on a second. I think I maybe miscounted. So there's 1, 2, 3, 4, 5, 6. Yeah, so this is -4. Sorry about that. So this is -4. So yeah, we are increasing. So that's good. How about over here? This is 4. This is also increasing. Okay. What else? We're also increasing from 4 to infinity. So that's here. So yeah, that matches. Okay. This matches as well. So, let's see. Decreasing, I imagine that would match for both. And then concave up, right? Decreasing, decreasing. Yeah, so those two check out. All right, what else can we look at? Concavity. So from -8, which is here, this is -8, -8, we are concave up. I'm sorry, from -8 to 0. So we're concave up. So they're both concave up. Yeah, so I guess this doesn't really help us too much. What else can we look at? So let's look at the sign chart. I suppose we can look at now these partition points for our first derivative at least. So my first derivative at x equals -4 has to be 0. But this kind of looks like the derivative doesn't exist because it kind of looks like one of those hard corners, or doesn't look like it's differentiable at those corners. Whereas on D, it looks a little more smooth in that I have horizontal tangent lines. And notice at 0, it's one of those hard corners again where my derivative is not a horizontal tangent line. So that's why D is going to be our answer here. It's a very subtle point. Because even if you looked at these function values, I bet they check out as well. Right, f of -8 is 0. F of -4 is -4. Oh, I'm sorry, this is -4. Let's see. So I guess the scale is 1 here. So yeah, -4, 0, 0. So yeah. So this question quite literally came down to looking at the partition points and their derivatives. So that's why this answer is D. Okay. Let's do one more. So we have a domain of all real numbers except -2. Except -2. So let's see, is all of these not have -2? Yep. So yeah, the scale is by 2 units. -2, so yeah, -2 is nowhere, so that's okay. The limit as we approach -2 from the left is positive infinity. So that means to the left of -2, we should be going up to positive infinity. This goes down to negative infinity. Same for this one, and same for this one too. So that pretty much leaves D. Let's look at the limit as we approach from the right. That should be negative infinity. So, I mean, they all have that except for C. So, I mean, C is really wrong. But D is the only one that have these two. And then the limit as x goes to infinity, so in the positive direction, yep, we have this horizontal asymptote in the positive direction of 2. So yeah, D is most likely our answer. We can confirm it further with our sign charts. I'm expecting my F to be increasing on negative infinity to 3. That's just reading off this blue part, and decreasing from 3 on. And let's see, we're increasing to 3. 3 is probably around here-ish. So yeah, we're increasing and then decreasing. That looks good. And then F is concave up from negative infinity to 2, -2, and 6 to infinity, right? When my derivative is positive, my second derivative is positive. And when my second derivative is negative, I have concave down on my F graph, and that's between -2 and 6. So let's check it one more time just to be sure, and for extra practice, I suppose. We want to be concave up to -2. Yep, you can kind of imagine it being concave up. And then from 6 to infinity, that's, I think, right here. So yeah, that looks concave up, and then everywhere else is concave down. So D's our answer. Okay, so now we have a function, x plus 2, x minus 2, and we want to try to find as much as we can about it as possible. So first, let's start with the domain. Domain is all real numbers except for what number? So except for what number is when x minus 2 is equal to 0, because we have that divide by 0 issue. And so that's when x is equal to 2. Right, you just solve for x minus 2. All right, x-intercepts, that's when my y is equal to 0, where my y is my f of x. And so we can multiply both sides by x minus 2 to get rid of that denominator. That makes the left side still 0, so x plus 2 or x minus 2. Okay, and then my y-intercepts, that's when my x is 0. So I'm going to plug in 0 wherever I see an x. And that gives me -1. Okay. All right, for this one, oh, did I skip it? That must be a copy of a slide. We're just going to skip. Okay, so the next part, we want to know the horizontal asymptotes. So for horizontal asymptotes, that's when you want to look at the degree of x plus minus 2, because we have a rational function. And so you would just take the coefficients since they're the same, they're both 1. So our horizontal asymptote is y equals 1. Okay. And so let's see, next, vertical asymptote. So this occurs when the denominator, we solve for the denominator equal to 0. Oops, minus 2 is equal to 0, so x equals 2. And yeah, remember to put it in equation form as they ask. All right, so now we're getting into increasing and decreasing. So you know what we're going to need for that? That will be the first derivative, right? So I think I'm going to rewrite my function just to make it a little easier. F of x is equal to x squared. I'm going to bring that x minus 2 upstairs, but when I do that, I have to make the power negative. So now I want the derivative of this, but notice that we have a product rule, right? Because I have one thing with x times another thing with x, so that means I need the product rule when I take the derivative. So when I take the derivative of the first thing, that's x plus 2. Then I rewrite the second thing, x minus 2 to the negative 1 power, plus I rewrite the first thing times the derivative of the second thing, x minus 2 as well. All right, so f prime, if I take the derivative of x plus 2, that's just going to be 1, right? 1 plus 0. So rewrite the x minus 2, negative 1, plus x plus 2. And so the derivative now of x minus 2 to the negative 1 power is negative 1. X minus 2 to the minus 2 power, remember, we're subtracting 1, so minus 1 is minus 2. And then chain rule times 1. So we can rewrite it like this, x minus 2. So I'm just bringing that back downstairs so I can have a positive power on it. Same thing with this term, x minus 2 squared, and then I have a negative, so that turns this into a negative. And I think that we will be needing the second derivative, so I'm going to simplify just a little. I'm going to combine these fractions just because I want it as simple as possible. So to do that, my common denominator is x minus 2 squared, so I'm going to multiply the left term, 1 over x minus 2 by itself basically, and get x minus 2, so like that. So I can combine these two fractions. Now they have the same denominator. And so I get x minus 2 minus x, distribute that negative in, just be careful with that, all over x minus 2 quantity squared. So I get these x's cancel, so I get minus 4 over x minus 2 quantity squared. And that is our f prime of x. Okay, so I want to know where is my partitions, right? My partitions are where my f prime of x equals 0 and f prime does not exist. So because my numerator is a positive number, there's no x's in there, this will never be equal to 0. But it will not exist when my denominator of my derivative is equal to 0. So I get x minus 2 is equal to 0, which means x equals 2 is a partition number. So let's pick a point before and after it to test it. So my f of 0 is negative 4 over 0 minus 2 squared. Well, that's just going to be a positive 4, which gives me negative. And then f of 3 minus 4, again, just plug in that 3 into my first derivative, square it. And I also get minus, right? Negative 4, so it's decreasing everywhere, right? It's never increasing. Well, it's decreasing from negative infinity to 2 and 2 to infinity. Okay. So let's see, find any local extrema. So kind of based on that last question where we had a sign chart that looked like this, or just saying that my f is pretty much decreasing everywhere, basically decreasing from negative infinity except for 2, I suppose. And so we don't have any local extrema here because there's no change in increasing or decreasing. So that's kind of nice. So as I predicted, we will need the second derivative to talk about concavity. So I think we got the f prime of x to be minus 4 over x minus 2 squared, right? And so I'm going to rewrite this like I did for f in this form, bring that x minus 2 quantity squared upstairs by making the power negative. So now I want the derivative of the derivative, which is our f double prime. And so that's power rule, right? Bring down the negative 2, rewrite the stuff in the middle, subtract 1, and then chain rule, derivative of x minus 2 is just 1. And so my derivative is negative 4, or positive. Negative 4 times negative 2 is a positive 8. And this is all over x minus 2 to the third power. Okay. And so let's look at partition points, right? So f double prime is equal to 0. So again, this is never, because I have a positive number. I don't have any function of x. So that my numerator will never be 0. Let's look at f double prime is not defined. That's going to occur when my denominator is equal to 0, right? So x minus 2 is equal to 0, or where x equals 2. So on my sign chart, I'm going to have a partition number of 2. So let's test 0 and 3. F double prime, remember to plug it into f double prime. I get 8 over 0 minus 2 cubed. So I get 8 over minus 8, so that's going to be a negative. And then f double prime of 3, let's plug that in. 3 minus 2 cubed, so that's going to give me 8 over 1. And so that's positive. So notice that this means that f is concave down, right? Because we're talking about concavity here. Concave down here, and then it switches to concave up after 2. Okay, and so that we'll go with B because it takes on both types. So it's concave upward from 2 to infinity, and then concave downward on negative infinity to 2. All right, so a point of inflection or inflection point, that is a partition point, recall, where concavity changes, right? But, this is a big but, it must be in the domain. The domain of f. And so remember our very first question, we were asked about the domain of f, and we said all numbers except for 2, right? Because that makes a divide by 0 error. And so there are no inflection points. If 2 were allowed in the domain, then 2 would be an inflection point because concavity changed. But it is not for this particular problem. All right. The very last question for this one, we want to put together all of that and make a graph. Okay, so let's see. Domain is that. All real numbers except for 2. It's kind of hard to tell. I think this is, each is 2. No, each is 1. 1, 2, 3, 4, 5, 6, 7. Yeah, each tick mark is 1. Okay, so here they do have something defined for 2, and that's not right because 2 is not going to be my domain. So A is not our answer. For the same reason, C looks defined, and it looks defined in D as well. So, I mean, that kind of makes our life kind of easy with B, because we said that there's a vertical asymptote at x equals 2, which I wish they would make these graphs a little easier to read, but that's 2, and that kind of matches with that part. Oh, I suppose I wasn't looking at the right point for this one. There is, wow, okay, so this is the axis. Okay, so yeah, this, sorry, D could be an answer. They need to like work on like maybe making these different colors or something. I don't know, it's kind of hard to read. But this is also 2. Okay. So A and C are at least out. What else? We know that these fit the domain. How about the intercepts? So x is equal to -2. So this one has an x-intercept. This is probably -2. Same for this one, maybe. Hard to tell. Maybe not as reliable. What about y-intercept? So this one has a positive y-intercept that I'm sure of, and it's probably positive y equals 1. So that is probably not it. And then this one has a negative y-intercept. So D, I believe, is our answer. We have a horizontal asymptote. This asymptote right here is y equals -1. Whereas this asymptote here is y equals +1. So that's another reason why D is right. F is decreasing on its domain. You can see B is increasing everywhere, right? D is not, D is decreasing, so that checks out. No local extrema. Concave down from here, right? That's concave down and then concave up after 2. And then a point of inflection at x equals 2. Or no, there's no point of inflection. I think this is a error. Sorry, no point of inflection, right? Because it would have been if 2 was in our domain, but it's not in our domain. So disregard that last statement. Okay, so D is our answer here. All right, let's try one more. It's just good practice. It's kind of similar. Let's see. So domain again, we can't put a +3 because that'll give me 0. You can just solve it this way if you like that better. X-intercepts, that's when my y is equal to 0. So that's x plus 3 over x minus 3. So when x plus 3 is equal to 0, and that's x minus 3. What about? Did not ask. Okay, horizontal asymptotes, pretty similar kind of function, right? So you look at the degree on the x's, on the highest x term. So 1 and 1, so they match. So you take the coefficients. It's like an understood 1. So y equals 1 is a horizontal asymptote. All right. What else are we looking at? Vertical asymptotes. So that's where we solve for x when the denominator is equal to 0. So x equals 3. All right, increasing, decreasing. So we'll need the first derivative. It's very similar to last question, so I'm gonna do it in a similar manner. I'm gonna rewrite f of x as this. Just bring that bottom quantity upstairs, make the power negative. So my f prime is going to be, again, a product rule. I see that I have a term with x multiplied by another term with x. So a product rule, and take the derivative of the first term, x plus 3, that's just going to be 1. I'm going to rewrite the second term, And then I'm going to add the first term, x plus 3, times the derivative of the second term, x minus 3 to the negative 1. So I'm going to bring that negative 1 down, rewrite the stuff in the middle, and then decrease the power by 1, that's minus 2, and then multiply by the derivative of x minus 1, or x minus 3, that's the chain rule. That's just 1. And so my derivative is this, if I rewrite it, plus x plus 3 over x minus 3 squared, and then I have a negative, so this becomes minus. So again, I'm going to find a common denominator, that's x minus 3 squared. So I'm just going to multiply that 1 by x minus 3 to get that. And so now I can combine my fractions like so. And so I get minus 6x minus 3 squared. So for increasing, decreasing, let's find our partition points. That's where f prime of x is equal to 0, or it does not exist, not defined. Never going to be 0, right? Because I got this negative 6. There's no x in the numerator. All right, it will be undefined when my denominator is equal to 0. So when I have this quantity, x minus 3 is equal to 0, or when x equals 3. So those form my partition points, or point. Move that down a little. Okay, so now let's test. What do you want to test? A point to the left of 3, that's easy, it's just 0. And then to the right, we can just do 4. So f prime of 0 will be negative 6. 0 minus 3 squared, that gives me negative 6 over, what, 9? So that's going to be a negative. And then f prime of 4 is negative 6 over 4 minus 3 squared, so that's going to be negative 6 over 1, so that's still negative. Okay, so my function is decreasing, it's never increasing, and this is on negative infinity to 3 and 3 to infinity. And because it's always decreasing, there's no local extrema. Okay. So concave up and down, and then inflections, so that means we're going to need the second derivative. I'll put the first derivative up here that we just found. Negative 6 over x minus 3 squared. And this is equal to, if we just convert it back to all in one line, so f double prime is negative 6, now power rule, minus 2, x minus 3, decrease the power, and then chain rule it. So I get 12 x minus 3 to minus 3, or 12 over x minus 3 quantity cubed. So let's find f prime is never going to be 0, right? Never. F prime is not defined, though, when x minus 3 cubed is equal to 0, when my denominator is equal to 0. And so this is when x equals 3. So if we do a sign chart of f double prime, now we can test 0 and 4 again, but now for f double prime. So just be careful you're putting it into the right function. And so we get 12 over negative 27. So it's going to be a negative number. Negative. And then f double prime of 4 is 12 over 4 minus 3 quantity cubed, which is 12 over positive, which a positive divided by a positive will give me a positive. So we have b, where it's concave upward from 3 on, right? Because my derivative, my second derivative is positive. And then it's concave downward from negative infinity to 3, because my second derivative is negative. And since the concavity changed, 3, x equals 3, might be a point of inflection, except what do we notice? 3 is not in our domain. So there are no points of inflection here. So not a point of inflection because it is not in the domain. And like the last one, we just want to find a graph that fits this description. So domain is all real except for 3. Yep. And so we want a vertical asymptote because they kind of go hand in hand. So let's look at 3. So this has a vertical asymptote at 3. This one has it at -3, so throw out A and throw out D for the same reason. The asymptote is in the wrong place. So B and C, x-intercepts are -3. Let's see, potentially it's kind of hard to tell, but yeah, I'd buy that. And I'd buy a little less for this one. Let's see about the y-intercept. -1. Yes, I agree, but this one has +1. Y equals 1 when x equals 0. I should just do 0, 1, right? That's this point. So yeah, let's throw out C. That's going to be B. Functions decreasing everywhere too. That's another thing. It's always decreasing, whereas C is always increasing. And then the function's concave upward from 3 on, right? And then concave downward before 3. And there are no inflection points, so B is our answer here. Alrighty, let's move on to a kind of application-based question where we have a cost function and we want to know the oblique asymptote of the average cost function. Okay, so we get obliques when the degree in the numerator, I'm just writing this down so you know, but when your degree in the numerator is greater than the degree in the denominator, then you have an oblique asymptote. Not sure if you've ever heard of one, but basically it's like an asymptote that's like a form of a line kind of, and then your function is kind of like skewed around it, kind of. Something like that. It's not a horizontal or vertical situation. Now it's kind of this skewed asymptote. But anyway, not as important that you understand what it looks like. So for this one, let's remember that our C bar, or our average cost function, that's just going to be our cost function divided by x. So we get our cost function of 19,000 plus 87x plus 0.03x squared all over x. And so to find the oblique asymptote, we can just divide these individually, right? We can separate these into different fractions, I guess. Like that. And then these x's cancel, and one of these x's cancel. So I'm left with this 19,000 over x plus 87 plus 0.03x. And for obliques, we would drop this remainder term. That's a remainder. And so our oblique asymptote is, it's going to be a line in the form of mx plus b. And so that's going to be our oblique asymptote. All right, let's try one more. So again, I want to find C bar of x is equal to C of x over x. So 16,000 now, plus 92x plus 0.06x squared all over x. And so I can separate these fractions. They're the same if I do this. Over x. x. And again, I can play the same game, cancel out these x's, and I can drop this remainder term. And so my oblique is 0.06x plus 92. Okay. Oops, too far. Okay, so we have a marketing research department for a computer company. They have a price and demand function like so. And we're concerned between a demand x between 0 and 85. And so we want to approximate, or they want to approximate revenue that looks like this, right? X times P. And so we want to graph R of X, I suppose. All right, so the first thing, the first noticeable difference is that all the endpoints seem to be different in some way, shape, or form. So I think that might be the easiest way to figure this one out. See how they all have different starting and or endpoints? So let's find what R of 0 is. We can just plug that in for X. Right? And 0, right? Everything drops out. So that means that I have the point 0, 0 on my graph. So that's definitely A and D. So let's get rid of B and C. And then let's look at R of 85. So let's plug in 85, 1404 times 85 minus 0.13 times 85 cubed. And so just throw that in the calculator. Don't worry about doing that by hand. So I get 39,503 and change. And so if we look at our very horrible scale on our axes, I believe each of these tick marks are 3,000. That's really unfortunate. So you just count up 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-ish maybe. So this is 30,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again here, this is 30,000. So notice how this endpoint, this right endpoint where x is 85, it's below 30,000. So there's no way that D is the right graph, because here it looks like that my endpoint, my right endpoint, is above 30,000. So, and it's probably right at 39 if each of these are 3,000. So A is our graph here. All right, one last application problem. So we have, what do we have? We have Silicon Valley now. Or in Silicon Valley, we have a water quality control agency. And this is the required monetary pool in millions of dollars. I'm not sure if that's important. Where percentage expresses a decimal fraction of the total contaminant removed. Okay. Oh, X is. Got it. All right, well, anyway, we want to know where P is increasing, decreasing, and then concave up and downward. So you know what that means. We're going to need the first derivative and the second derivative. So I'm going to get P into a very nice form. That'll make it easier to take the derivative of. All right. So try to get comfortable with switching out this like power to negative from the denominator, because it'll come in handy. P prime. So again, I have a product rule, right? 4x times 1 minus x and negative 1 power. So that's two terms with x being multiplied. So that means product rule. So let's take the derivative of the first term. That will be just 4. Take that coefficient, 1 minus x and negative 1. Then I'm going to rewrite my 4x. And then the power rule, right? Negative 1, 1 minus x. subtract a power of, or subtract 1 from the power, and then chain rule. So the derivative of x, or 1 minus x, is actually -1. So just be careful with that. So that gives me 4 over 1 minus x. I have two negatives here. They're going to make a positive, so I have positive 4x over x 1 minus x squared, like that. And then I'm going to combine them just because it'll be a little easier to take the second derivative. So common denominator is 1 minus x squared, that quantity squared, so 4 times 1 minus x over 1 minus x squared. That's how we convert this first term. So we'll be able to add it to the second fraction. So if I distribute that 4 in, I get 4 minus 4x plus 4x. Now I'm going to combine the two just in one step. So my f prime is equal to 4 over 1 minus x squared, and this is 4 times 1 minus x to the minus 2 power. I'm just getting it ready for the second derivative that I'm just going to take right now while we're on a roll. So f double prime 4, bring that power down, 1 minus x, subtract the power with 1, so that's 3, and then multiply by the chain rule, so again -1. So that gives me a positive 8 over 1 minus x cubed. All right, and I think that looks good. So now let's finish it off and find partitions for both. F prime is equal to 0. So in looking at this form, it will never be 0, right? Never. So f prime is not defined when my denominator is equal to 0. So that's 1 minus x quantity squared is equal to 0. So 1 minus x equals 0, or when x equals 1. So that's going to be on my sign chart. Let's test 0 and 2. So f prime of 0 gives me 4 over 1 minus 0 squared. That's going to result in a positive 4 over 1. And then let's try f prime of 2. That's going to be 4 over 1 minus 2 squared. That's still going to be positive, right? 4 over minus 1 squared, that minus 1 will become positive, so we'll have another positive. So it's just going to be always increasing from, I guess, I'll put it here, negative infinity to our partition of 1, and 1 to infinity. Okay, so for this last part, or at least on this question, let's find the partition. So f prime equals 0. Again, never, right? Nothing will make my numerator equal to 0. Prime is not defined when 1 minus x cubed is equal to 0. And 1 minus x equals 0, so x equals 1 again. Let's put it on my sign chart. Test 0 and 2, pretty reliable. And so my f double prime now of 0, when that is 8 over 1 minus 0 cubed, so that's going to be positive, right? 8 over a positive 1, positive. And then let's also look at f double prime of 2. That's going to be 8, 1 minus 2 cubed. So that's going to be 8 over minus 1 cubed, which is going to be a positive divided by a negative, which gives me negative, negative, negative. So we have the first case where we are concave upwards from negative infinity to 1, and then concave downwards from 1 to positive infinity. All right. But also, let's go back and just check because we were given a domain. So let's actually refine our answers just a little bit. We're only worried about from 0 to 1. So that means that we can actually just get rid of this part because we don't care about what's after 1. And we can change this left endpoint to be 0. So that's probably a better answer and probably the only answer MyLab will accept. So just be careful with domains. Be sure to check it before you answer it. And then for concavity, again, we're not considered what happens after 1, just before and between 0. So again, let's change this to 0 to 1. And so that might change. So now we're not concerned about concavity downward, right to the right. So actually, maybe we should go with B this time because we're only concave up on the given domain. So B for both. Yep. And pretty much the same answer, actually. That's interesting. Okay. Let's do C and D real quick. So vertical asymptotes, that's when you solve where the denominator is equal to 0. So x equals 1. Okay, so now for horizontal asymptotes, we look at the degree of our function, p of x. So the degree of the top is just 1, and then 1 minus x is also 1. So they match, so we take the coefficients. And so y equals -4. So on our graph, we have the horizontal asymptote of y equals -4 down here. But now we're only considering when 0, our x is between 0 and 1. So let's find the endpoints real quick. P of 0 is equal to 0 over 1. So 0, we know that the smallest value our function is starts at 0. Oops. So we know that we have the point 0, 0. And then we also found in the previous question from 0 to 1, our function is going to be increasing. So that's why our function does not have any horizontal asymptotes for this question. If we were considering the whole function, then potentially that would come into play, but not a problem here for long-term behavior. So let's find the x-intercepts. This is when y is equal to 0. So this is 4x over 1 minus x. So note this is when 4x equals 0 or when x equals 0. All right, and then y equals, for y-intercept, that's when my x equals 0. So I'm going to plug in a 0 wherever c and x in my function. And I get 0 over 1, which is 0. Right, and that kind of makes sense just given that we know that we go through the origin. All right. So let's put it all together and see what we got as far as making a graph. So we know that the x-intercept is 0, so is the y, so this means that we have the point 0, 0, as I mentioned. So I believe that doesn't look like 0, 0, but I'm pretty sure that's also not the answer. So D and C are out because 0, 0 is not on their graph. What else do we have? We have a vertical asymptote at x equals 1, and that's depicted in B. So B is likely our answer. We also know that P is increasing from 0 to 1. Both of them are. What about concave up? That's the big reason why B is correct, because this is concave up, this is concave down, so B is our answer. All right, hope you were hanging in there with me. I know that was a little bit longer and we covered a lot, but anyway, that sums up curve sketching techniques. And I believe the next section we'll talk about mins and maxes, extrema. All right, see you then.